All right, today we're going to be dealing with how triangles are similar when you use the altitude to the hypotenuse of a right triangle. So I guess first what I need to check on is, does everybody understand what the altitude to a hypotenuse is? Can you find that particular line if I draw you a figure? So first of all, what is an altitude? Yeah, it's the distance perpendicular from a vertex to a side. We also refer to that as the height of a triangle. So if I'm going to draw an altitude to the hypotenuse, I need to know what the hypotenuse is, and I need to know what an altitude is. So here's what I want you to do right now. I drew a little picture right here on the screen. In your mind, I want you to think which segment represents the altitude to the hypotenuse of triangle ACD. Think it in your mind. Is it in there? Did you think BD? Then you thought right. Does everybody understand what the altitude to the hypotenuse is? All right. So we have got a new theorem. That theorem is called the altitude to the hypotenuse of a right triangle divides the triangle into two triangles that are similar to the original and to each other. That's awesome. So if I draw the altitude to the hypotenuse, how many complete triangles did I just make? There's 3 total triangles there. And all 3 of those triangles will be similar. There's the big triangle, triangle ACB, and then there's the small triangle on the left, ACD, and then there's the bigger triangle on the right, but not the biggest triangle, CDB. You see the 3 triangles? So what I'm going to do in this next slide is I'm going to take this triangle that has an altitude drawn to the hypotenuse, and I'm going to write out all 3 triangles that were made. I'm going to orient them the same way, and then I'm going to make a similarity statement between the triangles. Because I just told you that if I draw the altitude to the hypotenuse, it makes 3 similar triangles. So let's see what the similarity statement would look like. So for this first triangle, this represents the big triangle. I left it oriented as is. And I'm going to call it triangle X, Y, Z. That means I go down the short leg, across the long leg, and then up the hypotenuse. So if I want to look at the other triangle over here, the short leg was YW, the long leg was WZ, and the hypotenuse was YZ. So if I want to orient it the same way, down the short leg, across the longer leg, and then up the hypotenuse, I have to position it. I have to basically flip this angle down so that it's YWZ. And that would be my similarity statement. I'm going to keep my corresponding angles in the same location. And then the same for this smaller triangle. XW is the shorter leg, WY is the longer leg, so it would be XWY. And that's an effective similarity statement. Everybody okay with that? All right. Keep the concept of an altitude of the hypotenuse of a right triangle in the back of your brain, and I'm going to change gears. And we're going to talk about something called the geometric mean. So, because in geometry I've created these similar figures, things are going to be kind of interesting when I start doing the ratios, because all of these triangles shared sides with other triangles. So even though on this smaller triangle I have XW and YW, YW is the same side in this triangle. So when I'm writing the proportion, XY to YW equal YW to ZW. When I'm writing out the proportionality statements, because they're sharing and using common sides, we're going to have what we call a geometric mean show up quite often. And a geometric mean is just that when I have the proportion a over x equal x over b, a geometric mean is when the two mean terms, the two terms made by the positive sloped diagonal, are the same. That number is called the mean. And in geometry, this happens a lot, so we have something called the geometric mean. So anytime I ask you to find the geometric mean of a number, what I'm really telling you to do is to take the two numbers that I want you to find the geometric mean of and set those two numbers up as extremes. Extremes are the numbers formed by the negatively sloped line in cross multiplication. And then set a variable up as the mean. So remember, cross multiplication was called the means extreme theorem. The ones that are along this diagonal are the means. And the ones that are along this diagonal are the extremes. So it's basically going to look like a setup of a over x equal x over b, where a and b are the two numbers that I'm asking you to find the geometric mean of. So what would we do to solve this? So when I cross multiply, I get x squared is equal to 90. And then what would I do? Square root. And x is equal to the square root of 90. Technically, it's equal to the square root of plus or minus 90. But why do you think I'm going to throw away the minus? Because you can't have a negative length, and this is geometry. By the way, I'm okay if you just skip down to that final step and say that the geometric mean is equal to the square root of a times b. Just multiply these two numbers together and take their square root, and that will always give you the geometric mean. So in your memory banks, you might want to star this formula. If you forget this formula, you can derive it by setting up the proportion and cross-multiplying and solving. All right, so let's see if you can find a geometric mean. I want you to find the geometric mean of 4 and 18. When you get done, check with your partner and see if they got the same thing. Finding the geometric mean of 4 and 18 is going to be the geometric mean will equal the square root of 4 times 18. When I multiply those two numbers together, I get 72. So for right now, since we're not simplifying, we could just leave it as the square root of 72. Is everybody okay with that? All right, so geometric mean is pretty easy. Let me just give you a couple of tricky ones. What would the geometric mean of 8 and 2 be? How would we work that? Everybody okay with just getting a final answer of 4? All right, now let me make it really tricky. What would the geometric mean of square root 8 and square root 2 be? So that's going to be the square root of the square root of 8 times the square root of 2. So that's the square root of the square root of 16, which is the square root of 4, which is equal to 2. Now, it's more complicated because it has more steps, but it's not more difficult because you're just taking the square root of 16 and then taking the square root of 4. You just got to know when to stop. And this one, we only took the square root one time. So even though this is a perfect square, we don't keep square rooting it until we're done. There's only one square root symbol, so we only take it one time. Here, there were two square root symbols, so I had to take the square root and then take the square root of that answer. By the way, when you multiply square roots, they both have to be inside a square root to be able to multiply together. If I had a 2 times the square root of 8, it wouldn't be the square root of 16. It has to be the square root of 8 times the square root of 2. Everybody okay with that? All right, easy so far, right? Yeah, we needed an easy day. Yes. Mackenzie, you okay with this? All right. So, now we're going to look at a corollary to the fact that we have similar triangles. Remember, if the triangles are similar, then things are proportional. So in the case of a right triangle where you draw the altitude to the hypotenuse, the length of the altitude to the hypotenuse of a right triangle is the geometric mean of the lengths of the segments of the hypotenuse. Well, that makes sense, doesn't it? So that means if I set up a fraction, the geometric mean is this line right here, and it's going to be repeated on these diagonals. And then the segments of the hypotenuse are this line, and they're going to be the extremes. Oh, wait, this is going to get confusing. Tell you what, has anybody ever seen a TV show where they had somebody hooked up to a heart monitor?
Yes.
Yeah, Grey's Anatomy. My favorite show. So, Grey's Anatomy, if you have somebody hooked up to a heart monitor, doesn't it kind of go like this? Beep, 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 beep. That was close. Beep. We're only going to be concerned with this part of the graphic.
Oh my God.
Okay? So, this right here, I'm going to call a graphic of a heartbeat. And I'm going to use this heartbeat graphic to remember how to set up something using this corollary. You know what? I'm not even going to remember these words. I'm just going to think heartbeat method. I was trying to get this lesson closer to Valentine's, but it didn't happen. So here's how the heartbeat method goes. Now remember, the pattern of a heartbeat is like this. Beep. So let's set up a proportion in order over the sides that I just traced. What was the first side that I kind of traced? So it's AD over CD. So I went up on the heartbeat stroke, and that got CD. When I go back down, it's going to get CD again. And then, what's the last one that I kind of traced over but missed? DB. And look, there's the proportion that's identical to this, which matches these words.
Wow.
Hopefully, remembering heartbeat will help you in setting up these proportions. Heartbeat. Beep. So let's practice this. All right. In this particular drawing right here, we have a right triangle with an altitude drawn to the hypotenuse. I would like to find the value of y. To find the value of y, since y involves the altitude, anytime you have the altitude involved in what you're looking for, it's going to be really good to do the heartbeat. So I'm going to do the heartbeat. I don't care whether you start at this end of the triangle or this end of the triangle when you draw your heartbeat graphic. I'll show you that it works out the same. So, beep. That's going to be 4 over y equals, what do you think goes up here? Y over 12. Now you might be thinking, well, Mr. Baker, what if I did it, what if I did it the other way? What if I did beep? That would be 12 over y equal y over 4. That's completely different than what you got. How in the world am I going to get the same answer? Well, when I cross multiply, this is y squared equal 48. When I cross multiply here, this is also y squared equal 48. It comes out the same way. Yeah. So, how do you solve for y? You just square root both sides and ignore the negative case. So y is equal to the square root of 48. So I use the heartbeat graphic to remember how to set it up. Once I set it up, I just solve for my variable. Are we okay with that? Oh, you're lost on the heartbeat? Okay, where did I lose you? Okay, so a heartbeat graphic looks like that, right? Okay, so if I were to take a triangle, and I were to draw the right triangle in such a way that this is the hypotenuse right here, and here's the right angle. And there's the altitude. So what I want to do is I want to set up a proportion involving the two segments of the hypotenuse and the altitude, and the altitude will be the geometric mean. That means the value of the altitude needs to go here and here. So if this were 4 and this were 12 and this were y, then I would go 4 over y equals y over 12. I'm just following the graphic, and that tells me what to put where in the order of this way. Does that make sense now? Okay. And I mean, once you get it, you get it. All right.
So how do you find x?
That's a great question. How do you find x? Well, x is going to be found by using this corollary. And this corollary says that the altitude of the hypotenuse of a right triangle separates the hypotenuse so that the length of each leg of the triangle is a geometric mean of the length of the hypotenuse and the length of the segment of the hypotenuse adjacent to the leg. So what that means is basically AC is the geometric mean between AD and AB, and CB is the geometric mean between DB and AB. Oh, that's a lot of. We need something better than that. We need a pattern. This pattern's a little bit messy, but I think it'll work. Has anybody ever thrown a boomerang? Yeah, I've never been able to get it to work correctly. Usually when I throw a boomerang, it goes out, and then it lands somewhere behind me. So this is going to be the boomerang method. All right, the boomerang method is always going to start in the center. So draw your triangle that looks like my triangle and put a big old dot on the center. Now, the boomerang method will allow me to set up a proportion involving either this leg or this leg, because this leg has some sort of relationship to the lengths of the hypotenuse, and this leg has some sort of relationship between the lengths of the hypotenuse. Depending on which leg I want to use, that's the, air quote, direction I throw the boomerang in. So let's say I wanted to make a proportion involving CB. So I'm going to throw my boomerang, and the boomerang goes out, and then comes back, but it always lands behind me. Boom. So the arcs define the sides of how I'm going to set up my proportion. So remember, this is the direction I went in. I went in this direction, and then I go back in this direction. The boomerang method. So here's how I'm going to set up the proportion based on that. I started at the center, and I went towards B. So that is DB. Over, I went up to here, BC, and now my boomerang starts to come back, BC or CB, it doesn't matter, BC, and then finally, my boomerang goes the entire length of the hypotenuse for AB. And so, AB and BA is the same thing. Just as long as you have the two endpoints, it doesn't matter what you write it in. All right, so out to B, over to C, back to B, back to A. That's the boomerang. And that is a correct proportion that goes with this corollary, because CB was the geometric mean. Notice that these two sides are the same side. Pretty neat, huh? I could also create the proportion that uses the geometric mean of AC. See if you can set it up by throwing the boomerang in the other direction and see if you can come out with the same proportion. All right, hopefully this is what you did remember, you always start in the center of the hypotenuse for the boomerang. You always start at the corner of a hypotenuse for heartbeat, but for boomerang, you start in the center. So now I'm going to throw it towards A. So what do you think my first length is going to be in my proportion? DA. And then the boomerang is going to keep going up to here. What do you think is going to be down here at the bottom? AC. And the boomerang comes back, so it gets AC again, doesn't it? And then it goes all the way to the end, because the boomerang always lands behind me. And that's what? AB. So there's my proportion.
So when do you know when you use the heartbeat method versus?
That's a great question. So if we look back at this example right here, remember we already found Y using the heartbeat, and the heartbeat always ties in with this altitude that's drawn. But now we want to find X. Well, X is one of the legs.
Are you going to use them both pretty much always?
Well, I mean, depending.
When you have to find like two variables probably.
I mean, I'm not going to say always, but I set it up in this particular example to illustrate both, yes. So in this case, to find X, X dealt with the leg of the triangle, so I'm going to boomerang it. Remember, if I'm dealing with the leg, if I've got values that will help me now, it would be silly to do it like this because I don't have this value right here. It's not a variable and it's not marked with a number. It's pretty much independent, useless with respect to this problem. So that is not the boomerang I want to use. I want to use the other boomerang. And the other boomerang is going to look like this. So how would it set up? Call it out. 4 over X equal X over, not 12. How long is this whole line right here? 16. I had to add the 4 and the 12 because segment addition says you add two segments together to get the entire length. Now I'm going to solve by cross multiplying. So X squared is equal to 64. What does X equal? 8. So remember before I found the value of Y was square root of 48, and the value of X was 8.
I know.
Hopefully no more. All right, so we've got this all set up. Now I want you to do one. Find the values of X and Y. I'll give you a hint. You need to use both the heartbeat method and the boomerang method to find those values. All right, let's go ahead and find the solutions for this. I think I'm going to solve for X first. What method, heartbeat or boomerang, would I use to solve for X? Boomerang. And so I'm going to throw the boomerang. The boomerang always starts here. I'm going to throw the boomerang toward the side where X is. So that's going to be 4 over X equals, boomerang coming back, X over, and I got to get this whole hypotenuse. The length of that whole hypotenuse there is 4 plus 5, which is 9. So that's X squared is equal to 36. X is equal to 6. Are we okay for that? Does that make sense? All right. So just as long as you keep everything straight in your mind, it's not hard stuff. Now, I'm going to use heartbeat to find Y. Mackenzie, why did I use heartbeat to find Y? Well, Y is, what is this line right here?
Yeah, I did.
This line is the altitude, and heartbeat always goes with the altitude. All right, so I'm going to heartbeat, I'm going to go boop. So setting that up, I'm going to do 4 over Y is equal to, now I'm going back down, Y over 5. Did that make sense? 4 over Y equals y over 5. So cross multiply, and I get y squared is equal to 20, so y is equal to the square root of 20. Is everybody okay with that? Anybody have any questions? All right, now let's take a look at the alpha dog problem of heartbeat and boomerang. This is the problem that separates the A's from the B's. Are you ready? Boom, it's a word problem. Guess what? You just joined the robotics team. I'm going to enlarge this so we can read it here. Yay. Robotics. All right. You are preparing for a robotics competition using the setup shown here. Points A, B, and C are located so that AB is 20 inches and AB is perpendicular to BC. So these lines are perpendicular, forming a right triangle. Point D is located on AC so that BD is perpendicular to AC. That looks like I'm drawing the altitude to the hypotenuse. And then DC is equal to 9. I've got to write a program for the robot, and I have to move the robot from A to D, pick up the plastic bottle at D, and then I guess I'm going to shoot up here and throw it in the recycling bin. All right? So how far is this length right here? So let's take a look at what we got. I'm going to shrink it back down now. So I'm dealing with a triangle, and I'm dealing with that length. I'm dealing with that length, and then I'm dealing with this length. Which trick should I use? Should I use a boomerang or should I use a heartbeat? And why?
Because you can get both of the sides you need with the middle one. Because you're trying to find a
Right. So the heartbeat would go up and over and would include BD. However, BD is no information for us. The boomerang would go green, yellow, yellow again, and then some of green, red. Okay? So the correct answer to what should we use is boomerang. So boomerang is going to start right here, and I'm going to go there, and so my proportion is going to look like this. AD over AB equal AB over AC. Everybody agree with that? Is that easy to see? Now here's the hard part. When I go ahead and fill that in, it looks like this. AD is X, AB is 20, and AC is the green and the red. The green is X, the red is 9, so that's X plus 9. Segment addition says when you have two lengths, you add them together. Yeah, that's going to be interesting. I'm gonna give myself a little bit more room to work now that I figured out the proportion. I think I'm gonna throw all this stuff away, and I'm gonna move this over here to where I've got some room to work with it. All right, and I don't care about this anymore, so I'm gonna throw this away. So now the problem just becomes solve for x. Now it's algebra. We're done with the geometry at this point. Now we're in the algebra. So when I solve for x, that's going to be x times x plus 9 is equal to 20 times 20. Would everybody agree with that? So that is x squared plus 9x is equal to 400. Everybody agree with that? Since I have a degree 2 polynomial and I can't just take the square root of both sides, I think what I'm going to have to do is set it equal to 0. And now I can factor or quadratic equation to solve. I think I'll go with the quadratic equation because right off the top of my head, I don't know what factor pairs have a difference of 9 that are factor pairs of 400. So I'll plug it into the quadratic equation. A is equal to 1, B is equal to 9, C is equal to negative 400. So that's going to be negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. Everybody okay with that? So I'll move that up to here to where I got some room to work with it. So that's negative 9 plus or minus. 9 squared is 81. Negative 4 times 1 is negative 4 times negative 400 is a plus 1600. 2 times 1 is 2. So that's negative 9 plus or minus the square root of 1681 all over 2. I'm hoping the square root of 1681 turns out to be a perfect square. So square root 1681 comes out to be 41. So that's negative 9 plus 41 over 2 and negative 9 minus 41 over 2. However, this is going to be negative 50 over 2. This is coming out to be a negative number. I'm going to ignore that one. Negative 9 plus 41 is a positive 32. 32 divided by 2 is 16. So the robot must move 16 inches. And that's the solution. So, this is what I would call a complex problem with lots of room for mathematical error, but it is not a complicated problem. There's just a lot of moving parts to it. There's a lot of steps. So that makes our answer 16 inches.
Now you gotta make it move 16 inches.
Yeah, and I bet there was another problem in the book where now we had to, after it turned, we had to decide how far it went here. And so knowing that this is 16, now you could do heartbeat with 9 and 16. All right.